We are live, sir. You can start, sir.
All right. So, welcome everyone. Hello. I think we have to pause this like we did last time. Hello everyone. Welcome to this live session. Glad that you could join us. So please post your queries and feel free to interact. I look forward to this interaction. Please post your queries. I'll be happy to answer them. Yeah, I look forward to this interaction. Thank you. Thanks very much for joining us, Mr. Tushar Pandey. Very good afternoon to all of you. Good afternoon, Tushar. How are things going on? All of you, it would be great if you would also let me know about your background. That will help me better address your queries and so on. That will help me better interact with all of you. So I hope you're enjoying all the lectures, the lecture modules and the assignments and the concepts that are being covered, because this is a fundamental course that the principles of signals and systems, which has implications for several courses later, both at the undergraduate level as well as the graduate level in the electrical engineering, electrical and communication engineering, circuits and many other departments, many other disciplines, I would say. So Abhishek Kumar, good afternoon, very good afternoon to you. Good that all of you can join us. Wonderful, it's a great experience to be with all of you. Yeah, so please tell me more about your experiences, more about your questions, if you have any queries and any feedback that you would like to provide that we can incorporate to improve this course further, that will also be greatly appreciated. Sonia, good afternoon, very good afternoon to you. Very good. So I hope all of you are able to go through the lectures and understand the lectures, and hope it is proving to be helpful in your either your preparation for the various exams or even in the courses that you're doing at your university and so on and so forth. So let me start by doing taking some of the questions. So there is a question from Sankirna Joge regarding HZ having a single pole at 0.9 and a single zero at 1.1. Is it single zero at 1.1? So we have to look at the Z transform and the inverse Z transform of this, and we have to look at what is happening. So for instance, you know that when you have a pole, right, pole at a point A, any point A, then the stability and the causality, these depend on the ROC, that is the region of convergence. So for instance, if you look at this h of z, that is z minus 1.1 divided by z minus 0.9. Now the only thing that you can say about this is that you have to know about the ROC before you can actually comment about the one can actually comment about the stability and so on, right? And the other aspect is inverse of hz is the time domain function, right? And h inverse of z is simply h z with z replaced by z inverse, so that corresponds, I believe, to h of minus n, right? So if you take, instead of the impulse response h of n, if you take h of minus n, that will give you h of inverse of z, right? So these are different things, right? So that probably should explain the query. So Tushar is working on series application for IBS AMI modeling, which is for high speed applications, helping a lot understanding basics of signals and systems. Wonderful, wonderful, wonderful. Great to hear, Tushar. Avinash, thank you for joining us. Thank you. Thanks for joining us. Thank you all for joining us. Do let us know your queries so that we can better answer them. There is a query from Padmavati. So I cannot understand. I can't understand inverse Z transforms, Fourier transform. Also, for a better understanding, please provide clear notes. I believe the notes that are there in the lecture videos. These are already being uploaded, so you can look at those, and you can look at any standard textbook and on signals and systems such as Oppenheim and Wilsky and so on and so forth. Inverse Z transforms and inverse Fourier transforms, I do understand these are a little bit tricky, so these will come with practice. I suggest you keep solving all the assignments, understand the assignment problems, assignment solutions, and also more importantly keep looking at other books, other problems. Try to solve as many problems as possible, and that will definitely help you improve your understanding of these concepts, that is inverse Z transform, inverse Laplace transform, and all these things. Help you understand all these things much better. All right. And what is the application? So there's a query from Mr. Abhishek Kumar. What is the application of Laplace and Fourier transform real life as well as signal processing? Explain with examples. Well, there are a lot of applications of the Laplace and Fourier transform. For instance, if you look at any signal processing, for instance, let's take a simple example. Let's say you're looking at signal processing in a wireless communication system, right? So for instance, such as your 4G OFDM, orthogonal frequency division multiplexing, right, which is basically LTE, and the waveform used in LTE, that is based entirely on your FFT IFFT operations, right? IFFT. So that is an example of signal processing. Then you have your multiple input multiple output systems, and then so high-speed wireless communication is made possible by the advances in signal processing. Similarly, your image processing, right? When you look at images and try to process images, such as improve the clarity of images, denoise images, stabilize images, all of these are signal processing applications, right? Where you use the spectrum, the Fourier transform, and so on, and all these concepts. So signal processing, for instance, in a camera, right? When your camera takes a picture and you're trying to improve the quality, the camera in your mobile phone takes a picture and you're trying to improve the quality of that picture. So all of these are indeed applications of signal processing where you use these transforms, the spectra, and these are essentially tools that help you achieve process the signal, right? So these are indeed very important and fundamental concepts. Deepa Jain, classes are excellent. This has helped improving our fundamental concept signals and systems working in the area of adaptive signal processing. Wonderful, Deepa. Good to hear that you're finding the classes helpful. Glad that you're able to get a better understanding of the concepts of signals and systems. It's good that you're able working in the area of adaptive signal processing. That is in fact indeed a very interesting area, and it's an advanced area. So I wish you all the best, and do in fact look at applications of adaptive signal processing in areas such as, for instance, wireless communication, modern maybe 4G, 5G systems, and also probably machine learning and so on. So Tushar Pandey, hypothetical question: can we make an LTI system with number of zeros more than the number of poles within a specified bandwidth? This is a slightly complicated question. I'll have to look into the answer of this. But a priori, I'm not really sure about this. I will try to see if there is because this is really a more of a design kind of a problem. I'll try to look into this, see what possibly could be the solution. Is it possible to incorporate Matlab solutions along with your lectures? It would help us better understand the concepts. Avinash, please suggest some books having Matlab systems and signals and systems application. Avinash, unfortunately, due to either I would say the limited time or the limited support that we have, it's not really possible to incorporate the Matlab sessions at this point. Regarding books for Matlab application signals and systems, I am not really, I mean, there must be many books, but the best place to start with is just the Matlab help itself, because Matlab has many commands such as the FFT, DFT, and for instance things such as convolution, which is the command conv, and many other things such as I believe even pole zeros, and of course tools for plotting the spectrum and so on and so forth. So my suggestion is the best possible way to learn Matlab programming, especially for signals and systems, is to try to understand an operation better. For instance, if you want to understand the convolution, or if you want to understand the spectrum, then you simply look at what are the different commands for that and try to take some example signals and start with that in Matlab. So it's really really a very kind of how do you put it, very something that's where Matlab is something that's readily accessible, and one should be you should be able to easily look and understand several commands and apply them without much effort. Why final values theorem is not having it's not applicable for system having poles on the imaginary axis or right hand side? Not really sure. I'll have to take a look at that. Can we get a participation certificate for this session? I am not sure about that, because the certificate is probably given only after the exam. Why are we using multiple transforms if the best results come with only two? Correct me if I'm wrong. This is a good point. So traditionally, although we study a lot about the Laplace and the Z transforms, because these are sort of more general, and these, as you know, the Laplace and Z transform also exist when, for instance, the Fourier, the usual Fourier transform does not exist. But in practice, typically the transforms that we use are the Fourier transform, and the continuous time Fourier transform, the discrete time Fourier transform, the DFT, and also the fast implementation, the FFT. So I would say for a rigorous treatment of the subject of signals and systems, we do continue to, and of course these Laplace transform and the Z transform, these have applications in other areas, such as, for instance, your control systems, analyzing the stability of a system, and so on and so forth. Right, so looking at the poles, analyzing the stability, and especially when you have feedback loops and so on and so forth. But indeed, the Fourier transform is the Fourier transforms are what are very popular, especially in signal processing, and these are what are used extensively in practice. Right. So Shubhangi Sahu, it's good to join us. Pradeep Kumar, Sonia, Avinash Mohapatra, thank you for joining us. Do let me know also a little bit about your background, so I think that will help me better understand what your background is, and also do let me know if you have any feedback for the different lecture modules and anything, and what else you would like to. Could you please applications of signals and systems, mechanical engineering, it's only in the field of testing, like collecting data while DAQ system. So again, signals and systems is a concept that is very general, that has applications many domains, as I said, as I just pointed out. When you look at mechanical engineering, you have several systems that can be modeled as control systems, and you have an input, you have an output, you have a feedback, you have feedback loops, and so on. And then you look at the input, the relation between input and output of the system, or the output and input of the system, model it by a transfer function, and ask about what is the response of this system to the different inputs. Is the system stable? Is the system causal? And so on and so forth. And so definitely a lot of applications, in fact, even in mechanical engineering. And now, of course, with digital processing becoming commonplace in many mechanical and aerospace systems, signals and systems are, for instance, things such as be it either your automobiles or aeroplanes and so on and so forth. So signal systems, definitely the concepts definitely have immense application in, I would say, all disciplines of engineering, right? So when you're trying to solve the problem from standard textbook signal, we can't solve in first term, but when you see the solution of this problem, realize I know how to solve this. So as I also already pointed out previously, Mr. Balakrishna, thank you for joining us. The point is, these come with experience. So you have to, so there is really no shortcut to this. The point is, you have to keep solving. One recourse I would suggest is to diligently or carefully solve all the assignments. Make sure that you do not look at the solutions, but of course, because if you're looking at the solutions, then what happens is you get there is a tendency to sort of there is a tendency that you do not fully understand the concepts, or at least the application of these concepts. So if you really want to test your improve your application, try to solve the problem and keep going at it until you're really able to solve it. And once you solve a few problems on your own, you'll really get a much better idea of how to solve similar problems, and in fact also tackle, and you'll get the confidence to tackle more challenging problems in the future. So I would say don't directly rush to the solution, but try to solve to the extent possible, try to solve each and every problem, uh, try to solve each and every problem without it looking at the solution, and slowly, once you become more and more experienced, you'll gain a better understanding of how to solve. You'll become more comfortable at solving these problems and getting, and that in turn will give you a much better understanding of the concepts. So Darshan Kavaria, my question is, when you try to solve signals from standard X we can't, but when you see a solution, is there any solution of this problem? Okay. Again, Darshan I think has a similar question, which is essentially how to solve the problems without looking at the solution, and the only and the advice that I have to offer is basically, please try to solve problems on your own, and the more problems you solve on your own, that will build your confidence, and that will also help you get a clearer understanding of the concepts, and help you solve problems further, help you solve problems. Wonderful. There is a question regarding UT convolved with U minus T. UT convolved with the U minus T, so UT convolved with U minus T, so I believe that is going to be unbounded, because when you look at UT and U minus T, it's easy to see. There's a question from Mr. Akash Verma, what is UT convolved with U minus T, and that will be unbounded, because if you look at the area under that convolution, it is not bounded. Probably you can take a look at it, or maybe the TAs can take a look at it. So Abhinash Mohapatra, I'm a mechanical engineering graduate working in heavy construction machines domain. Took this course for my interest cause my responsibility included testings of machines and collecting data. Wonderful, wonderful, Abhinash. Good to hear this, and hope you're finding the lectures helpful. It's very interesting indeed that you're working in mechanical engineering, in the discipline of mechanical engineering, and particularly pertaining to construction machines. So glad to hear. It's very interesting that you find use of the principles of signals and systems in analyzing the data and testing and for analyzing the data that is collected, and also for the testing of machines. Wonderful, wonderful. Good to hear that. Excellent, excellent. Very good. Very good. So anyway, please do let me know your queries, and I will be happy to interact with you further. Jansi Rani, good afternoon sir, enjoying all the lectures. Is they're good as it can get, like all other course and sessions I've attended. Very good, very good. Good to hear from you, Jansi. It's great, good that you're enjoying the lectures. Can you graduate finding the lectures helpful? Can you take one more live session post covering all the lectures and assignment? We have much clear idea. Unfortunately, it will not be possible to cover the all the lectures and assignments in one live session, because as you can see, we have about roughly 36 to 40 hours of lectures, and several assignments. So I'm sure it's not going to be possible to cover all these assignments and lectures in one live session. But the point is the following: we have the lectures and the lecture notes, as well as the assignments, and more importantly also the solutions. So I think that should give you a fair idea of what the problems, how to attempt the problems and how to solve, and the solutions. And if you have any query apart from that, you can always post it on the forum, and the TAs will respond to that. I think a live session, because of the breadth of the material, it's kind of difficult to cover the entire material in one live session. Right, so there is a question from Mr. Abhinash Mohapatra regarding the final exam. It's a good question. The final exam will be online. right? I hope all of you have registered for the final exam. It's going to be online. Problems are going to be multiple choice, the same pattern as what you're seeing in the assignment. Each question followed by 4 options, and you have to choose one of the options. And some of the questions will be similar to what you've seen from the assignments. Some of the questions will be recall type, simply recalling the principles and definitions. Some of them will be similar to identical to what you're seeing in the assignments, and some will be different or open, but more or less related, modified versions of what you've seen in the assignment, right? So you will have, so if you are able to solve all the assignment problems, if you are able to understand the assignment problems and their solutions, you should be able to comfortably attempt and successfully solve and also get a good score in the exam on signals and systems. So this is simply to test your understanding of the various concepts that have been covered in this course. So the exam is not going to be particularly tough or grueling, but rather very similar to the kind of include problems, very similar. The format is identical to that in the assignments, that is multiple choice questions, and the nature of questions is going to be very similar to what you are seeing in the assignment. So I encourage all of you, I hope all of you have registered for the final exam. So Mr. Subhangi Sahu, I am working as an IT consultant and resumed my studies electrical engineering MSc in Germany. I am revising signals and systems where this course is helpful, but with multiple transforms it is now a little hectic. Excellent, Subhangi, glad that you will be resuming your studies, and good that you are finding this course helpful. That is fine indeed. It's a little tough because we look at the entire content of signals and systems as is prescribed in a standard undergraduate course, for instance, both at IIT-Kanpur or in any of the universities across India, and more in line with the kind of syllabus that we have for the GATE examination and several other competitive examinations. So this is more or less the standard syllabus that we have for the signals and systems course at an undergraduate level to prepare for either the college or university level exams or also the competitive exams. So this is a little intense, I do agree with that, but you should still be able to get a lot of I mean, once you do this, they should give you a much better idea of the various concepts of signals and systems and help you prepare much better for the future courses that might come at the graduate level, such as be it in wireless communications, advanced signal processing, image processing, or machine learning, and so on and so forth, right? So yeah, I do agree that it can be a little hectic, especially if you are not able to devote some time to it, because at the end of the day, this is a fundamental course, and there is a significant amount of content being a fundamental course, and naturally one has to devote time to it to appreciate it, to appreciate these things better, right? All right. Very good, everyone. So welcome, good to hear from you. Do let me know if you have any questions, do let me know if you have any feedback, and do let me know what your interest is, what you're doing, and how are you finding the lectures, how are you finding the assignments, any particular queries that I can address, any particular aspects that we can incorporate either in this run or the future run, and so on. Which book is best for problems, Oppenheim or Ashok Ambardar, Simon Akin? First, suggest from any from your side for best problems that can improve my confidence. Very good, Balakrishna. I think it's a good point. I would suggest the book by Oppenheim, because that is one of the respected textbooks on signals and systems, not just in India but across the world, and that has been a long-standing book. In fact, it is a book that has been, I think, written many years ago. It's a book from which, for instance, that was a reference book even when I was a student, undergraduate student studying signals and systems, and continues to be a standard textbook which is used worldwide, across in the best universities best universities in their classes on signals and systems across the world. So I would highly recommend the textbook by Oppenheim, because although it might be a little strenuous to go through it, because it's a fairly rigorous and a fairly sort of, how do you put it, the treatment is, it's more like a treatise, and the book is quite voluminous. But I would say if you can go through several of the key aspects to the extent possible. That should give you a much better and solid understanding of the principles of signals and systems, right? And of course, any other book should be also good. For instance, the book by Haken should also be good, and then doing the problems and so on. But the idea is one should keep doing, really going through as many good books as possible, trying to solve as many problems, and in turn that will give you the confidence that will help you develop and build the concepts. Very good. Will there be any live session before the final exam to clarify rest of the queries of the remaining weeks? I believe not, because the queries and all those things particularly pertaining to the problems etc. will be directly addressed. For instance, in the forum you can just directly post them online in the forum for the class, and they will be answered by the TAs and so on. Which book do I need to solve for problems to excel in GATE examination? Again, I would say there is no one particular book that I can recommend, but I would say for a competitive exam, one should start with the idea to get a good grasp of the concepts, and then try to look at as many books as possible, try to solve. So you should have a really sort of insatiable appetite for problem solving. Try to take several books, look at several problems, try to get the solutions. So the idea is keep solve, keep working on them, and keep attacking as many problems as you can until you really master all these things and you become confident and become experienced. So that should be the approach. So the more you work hard, the more you strive, the better you will become. So I wouldn't recommend a particular book again, but as one of the previous persons had pointed out, Mr. Balakrishna, I think Oppenheim is an excellent book, Haken also, and both of these are respected books. In particular, Oppenheim is a book that has been used, that has been standing now for several decades in fact, and so a very respectable book, which is definitely, competitive exam or not, every student of the discipline, that is someone who's doing the course on signals and systems, should definitely have a copy of the book, go through that book and try to understand the concepts and the explanations to the extent possible, and also solve the problems. So wonderful. Good. Hari Praveen, thank you very much for your question. Good to hear that many of you are able to participate and able to ask questions. So for DFT, which textbook problems to solve for GATE preparation? That's a question from Tasneem AS. Again, as I said, I'm not really sure about GATE preparation, because see, we do not look at the classes from the perspective of preparing for a particular competitive exam, because these are the concepts that we teach in the classes at for instance IIT and so on, and when we do them, we use the standard textbooks such as either Oppenheim. I think that's the best textbook that comes to my mind. In particular for GATE, I mean, or any other particular competitive exam, there might be many books that might focus on each particular exam, or that might be written in a style that suits a particular exam, or covering some of these aspects finer. Although I believe the syllabus that we cover in this course should be suitable for a wide variety of competitive exams, because most of these concepts are fundamental and the coverage is comprehensive. I don't have any particular recommendation of either books for, especially pertaining to books for a particular competitive exam, right? So I cannot unfortunately recommend any particular book for a competitive exam, simply because I do not know of any books for the target beyond the textbooks, beyond the fundamental textbooks. Not really sure of some of these other books that target particular competitive exams, because essentially we do not use these for teaching purposes, while you might use them for preparation for competitive exams. Purely for teaching, that is teaching these concepts and teaching these courses in a fundamental fashion, I think they are not very suitable, right? So wonderful everyone, good to hear all of you. Hope many of you are preparing for both exams at the university level and also for different competitive exams, or preparing for higher studies. Good to hear that you're finding these useful. Please do let us know your questions, do let me know your feedback. As I've already said, the final exam is going to have multiple choice questions, questions with 4 options, very similar to the format that you have in the assignments. Many questions are going to be directly from the assignments, or the rest of them are going to be very similar, or slightly modified or enhanced versions of the questions that you have in the assignment. So you should be able to, if you're solved the assignments, understood the solutions to the assignment problems, you should be very comfortable, or you should be able to comfortably solve the problems that are being asked in the exam. And in particular, that should also help you better prepare for several competitive exams as well, because the syllabus, as I said, is modeled mostly along the lines of the GATE syllabus, which is again very similar to the syllabus that is there for many other competitive exams. There might be minor variations here or there, but by and large the syllabus, the syllabi are overlapping to a great extent. Very good, everyone. Good to hear that. Hope you're finding the lectures useful. Please do let me know your feedback. Do let me know if you have any other questions or any other recommendations, or thank you, Avinash. Thank you. Thanks. Thank you very much. Thank you. Let us try to solve a simple problem, if you can. So I hope all of you can see this. So I hope all of you can see this. Right, so I hope all of you can see this. Let us call this as the pulse h of t. The question is, what is h of t convolved? What is h of t convolved with itself? Can someone tell me what is h of t convolved with itself? What will be the output when h of t is convolved with itself? What is the, so I hope all of you can see the question.
Yes.
So there is a simple question that I've written, that it is a pulse. Mr. Rajeshwari, thank you. Ms. Rajeshwari, thank you. Thank you for joining us. It's a good question. It is possible to do research in signals and systems. Yes, indeed. Yes, indeed, because signals and systems are such a fundamental area that it has many implications. For instance, even if you look at either wireless communication, if you look at signal processing, if you look at image processing, I mean, the applications of signals and systems are everywhere. I mean, everywhere you take a Fourier transform, everywhere you take an FFT. For instance, you have a large data set, you take the FFT, try to design a machine learning algorithm or a classifier in the spectral domain. Then we are applying the concepts of signals and systems, right, in machine learning. So definitely it is very possible, and knowledge of the signals and systems is very important to do research in many domains, including wireless communication. When you're doing, as I said, just pointed out a little bit better, that is a little bit earlier, that is when you have, for instance, OFDM, you're using the orthogonal frequency division multiplexing, that is based on concepts of signals and systems. Yes. So what is the answer to that question? I've given pulse HT convolved with HT. Sonia, that's good. Answer is triangular, but can you be a little bit more specific about what kind of triangular Bobby, what is, thank you for Bobby Buddy, thank you for joining us. What is the physical meaning of convolution of the two signals? So the physical meaning is the convolution essentially is two things. One is that it tells you the impulse, the response of the system to an impulse, and it tells you if the input is a certain signal, then what is the output. It is given by the convolution of the input and the response. An excellent example of this would be, for instance, a wireless communication system where you have a channel. The channel is basically has the impulse response ht, and then you transmit a signal that is your xt, for instance, let's say from the base station, and then the signal that you get to your mobile is essentially xt convolved with ht, right? So that is essentially the output, right? So, and there are many such applications. For instance, you have an image, you apply a filter, and you ask what is the output. The output is basically the image response of the spectrum of the image multiplied by the response of the filter in the frequency domain, and in the time domain or in the spatial domain it would be the convolution, right? So I think people have got the answer. So this is triangular from 0 to 2 with peak at so this is triangular from 0 to 2 with peak at 1 of value. What is the peak at 1? I am not sure if the value of the peak at 1 is correct. Can you please correct that? What is the value of the peak at 1? Can you please correct the value of the peak at 1? That is triangle with height 2 width 2. Sonia, triangle with height 2 width 2. I think the width 2 is correct, but the height 2 is not really the height, as Jansi is saying, that's correct. The height is 4. So at the peak, when they completely overlap, you have 2 into 2, that is 4, and 4 into 1, and 4 into 1, that is essentially going to be, that is 4 into 1, that is essentially going to be this thing. And now let us look at another thing, that is triangular pulse with duration 2, maximum amplitude 4. Very good, good, glad. Now let us look at what is ht convolved with minus ht. Let us ask that question. What is ht convolved with minus ht? Can someone tell me what is ht convolved with minus ht? ht convolved with minus ht. Correct. I think many of you have got the correct answer, which is the peak value is 4, and it's a triangle with height 2. Height is 4 and width is 2. Very good. Correct. I'm asking now, what is ht convolved with minus ht? ht convolved with minus ht. So we have seen ht convolved with ht. What is ht convolved with minus ht? ht convolved with minus ht. What is the output when ht is convolved? Balakrishna Ketani, that's good. So what is ht convolved with minus ht? Anyone? Can anyone explain what is ht convolved with? ht convolved with, I'm sorry, ht convolved with h of minus t. ht convolved with h of minus t. ht convolved with h of minus t. Jansi Rani, I'm sorry, I probably misspoke. I said ht convolved with minus ht. That's not correct. I meant ht convolved with h of minus t. That is what I meant to say. My apologies. ht convolved with h of minus t. You are correct. If ht is convolved with minus ht, then it will be the same with it will be the negative of that. I'm saying ht convolved with h of minus t. That is what I'm saying. ht convolved with h of minus t. ht convolved with h of minus t. ht convolved with anyone? ht convolved with h of minus t. If ht is the pulse from 0 to 1, what is ht convolved with h of minus t? What is going to be the peak, and what is going to be the spread of ht convolved with h of minus t? Balkrishna Khetani, good matched filter. I'm just asking what is the output of the matched filter? ht convolved with h of minus t. What is the output? Rajeshwari, amplitude is 4. Very good. Very good. Amplitude is 4. Very good. And what is the spread? I mean, what is the shape and the spread? So the peak amplitude you mean, right? The peak height is 4. Balkrishna Khetani, triangular pulse from -1 to 1. Very good. Very good. Very good. Very good. Very good. Very good. Peak is 4. Excellent. Excellent. In fact, this is a matched filter peak from -1 to 1, and this is, in fact, this is going to be as you have rightly put it, this is going to be that's correct. So correct. So very good. So good. So let's see, let us try to do another example. Let me try to cook something up to engage you. Let us consider this. Should I write on this?
Yes, also next page also you can write.
No, I can write next page, but
yes.
I can just choose this, right?
Yes.
So 2z by z square minus, let's see, let me try to see if I can get this right. Z square minus z square minus 6 z square minus 6z plus 8. This is your h of z. What is the inverse z transform of a stable system? What is the inverse z transform of a stable system? So this is 2z by z square minus 6z plus 8. What is the inverse z transform of a stable system? what is the inverse Z transform? What is the inverse Z transform? Well, Krishna, there are some questions. I think what happens if the filter is non-causal? When the filter is non-causal, it cannot be applied in real time. That's the only thing. That is, you cannot apply it's non-causal filter. It's a good question. You can apply non-causal filter as long as you have the signal that is stored, like for instance, an image or something that the operations can be non-causal, right? But you cannot apply it in real time. For instance, let's say your signal, you're running a vehicle and you're collecting or you're in an aircraft and the signal is coming in an aircraft and you're trying to real time trying to process the signal and analyze that. You cannot use a non-causal filter. One can only use causal because you can only use the past samples, you cannot use the future samples. Gibbs phenon is good for any signal, correct, which has the sharp edges. So essentially it means that you should have a larger and larger number of sinusoids to approximate any particular advantages or no advantages. Sonia, 4 to the power of n un minus 2 to the power of n. It's good. I said what is the Z transforms? Good, Sonia, that's good, very good. Happy we have to have the answer, but can you just correct your answer a little bit, because I said the Z transform of a stable system. Remember, we need the system to be stable, and this is the trick. So it's very good. So at first you might really get confused with the answer, because you have to really look, because remember, this is the important thing. Whenever I give you a Z transform, I have to give you the ROC, right? Because without the ROC there can be multiple inverses, right? And that is the whole point. And now I have given you a Z transform. I have not given you a ROC, but on the other hand I have given it's a trick, right? I've told you that it corresponds to a stable system. So now you have to tell me what is the stable system corresponding to this. There are many systems. What is the stable system corresponding to this? What is the stable system corresponding to this? Tasneem AS, very good, excellent, excellent. That is the answer. 2 to the power of n u minus n minus 1 minus 4 to the power of n u minus n minus 1. Very good. So that is the answer. So what you get is, I hope all of you are able to appreciate it, which is, if you look at this, you can write this as h of z by z. H of z equals, I think most of you got that. That is, you can write this as z by z minus 4 minus z by z minus 2. I believe that is correct. Yeah, and now if you look at the stable system, the inverse becomes, this will be minus 4 to the power of n u minus n minus 1 plus 2 to the power of n u minus n minus 1. So that is the important thing. And what this problem clearly shows is that one should not rush to go to the solution, but you have to read the question completely, right? Sometimes it's easy to come up with a simple answer. I know that this is in fact the trick that I use. I know the tendency is to immediately go for the answer 4 to the power of n un minus 2 to the power of n un, because that is the simplest thing you can think of, is a raised to n un. But that and this is the trick in competitive exams, right? And this is what you have to appreciate, right? The questions are more or less, they are going to be the same, but they are going to be a little tricky, right? You have to read the question completely before you jump to an answer, right? Sometimes the simplest answer, you get a feeling that once you solved it, go for the simplest answer. Sometimes that might not be the correct answer. You have to read the question completely before you get the answer, right? Thank you so much for the detailed explanation. Signals and systems, is there any negative frequency? Yeah, so negative frequencies, essentially you can think of these as the images, right? So whatever the frequency that you have, the component, the same component is present in the negative thing. For instance, a sinusoid. So if you have a pure frequency component, positive frequency, in fact it's not a real signal, right? Like a complex exponential. any real signal will both have a positive and the negative frequency, the image, right? For instance, a sinusoid has the positive component as well as the negative component, right? So these two come in complement, right? So very good, thank you, thanks very much. Hopefully you're good. So are you able to understand this question, everyone? The question that I posed, that is the inverse Z transform, or is there any need for any clarification? Is it clear? Now if I tell you I want the Z transform of inverse Z transform of an acausal system, for this question, same question, if I want the inverse Z transform of an acausal system, what is the inverse Z transform of an acausal? What is the inverse Z transform? So for the same Z transform, if I want an acausal system, same Z transform, if I want an acausal system, what is the impulse response Hn? Can someone tell me, if the same one I want an acausal system, what is the Z transform? For the same one, if I want an acausal system, that is H of Z, same expression that I have given before, if I want the system to be acausal, what is the inverse Z transform? If I want the system to be acausal, if I want the system to be acausal, what is the inverse Z transform? Okay, anyone? If I want the system to be acausal, can someone tell me what is an acausal system? So these are the kind of challenging questions. I wouldn't say challenging, but these are the kind of, trick questions that one would face in competitive exams, or maybe sometimes even in your university level exams. Some of these questions are very similar. They just you have to have a much deeper and complete understanding of the concepts of signals and systems. So what is an acausal system? Can someone define to me? All of you are, I'm sure, are brilliant students. Many of you are undergraduate, some of you must be postgraduate, working and so on. Some of you must be preparing for competitive exams also. So what is an acausal system? Can you tell me what is an acausal system? What is an acausal system? Anyone? Tasneem, Rohit. What is an acausal system? Sonia, depending on past history. Rohan Garje, a system where output depends on past and current inputs but not future. I'm not talking about causal. I'm talking about acausal. A-C-A-U-S-A-L. Acausal, or probably you can call it acausal system. Acausal, not anticausal, an acausal system. So you have causal, you have anticausal, and you have acausal, right? What is causal? Causal is only when it depends on the past and current. Anticausal is when it depends on the future. only. And acausal is when it depends past, future, current, right? That is an acausal system. Okay, you get my point? So an acausal system, if you can do a quick Google search, an acausal system is not a causal, it basically depends on past. A causal system, right? An acausal system is a system with output depends past, current and future also, right? So this is an acausal system. So I'm saying what is the acausal system, right? If it depends on the impulse response of an acausal system, right, where the output depends not only on the past and current but also future. So there should be a dependence on the past, current and as well as the future, which means essentially the impulse response should span from minus infinity to infinity. Right, I think Tasneem got the answer. What will be the ROC of this acausal system? Of an acausal system, what will be the ROC? So acausal, I think another way to think of the acausal is that it is neither causal nor anti-causal, and then you call it an acausal, right? Neither causal nor anti-causal, right? Causal, Hn is only 0 or is non-zero for n greater than or equal to 0. Anti-causal, HL is non-zero for n less than 0. Acausal, Hn is non-zero for both n greater than or equal to 0 as well as n less than 0, right? So that is your acausal. What will be the ROC for this acausal system? As you can clearly see, the ROC has to be of the form, if it is to span minus infinity to infinity, not left-handed but right. The poles are minus 4 and 2. So acausal system will have the ROC 2 less than magnitude of z less than 4. This will be the ROC for the acausal system. So if this is the ROC for the acausal system, naturally the inverse z transform for the acausal system will be, since magnitude of z less than 4, so that will be, I believe, if magnitude of z is less than 4, so that will be, I believe, minus 4 to the power of n u minus n minus 1, and magnitude of z greater than 2, so that will be minus 2 power n un. So that will be the acausal system. Okay, so that will be the acausal system. Okay, so the ROC will be minus z less than or equal to 2. So ROC, that's correct, ROC is 2 less than magnitude of z less than 4. And finally you have the causal system. And what is the inverse z transform for the causal system? And that is, I think, what everyone answered initially, that is 4 raised to the power of n un minus 2 raised to the power of n un. That will be the ROC of the causal system, but the causal system is not stable, and this is something that you have to remember, something that's very important. Both the causal system and the acausal system in this case are not stable. Only the anti-causal system. So if someone asks you what is the system which is stable out of the causal, acausal and anti-causal system, which of these system is stable? Can someone tell me which of these systems is stable in the causal, anti-causal and acausal systems? Among these, which is stable? What is the criterion for stability, by the way? For the Z transform, what is the criterion for the stability? What is the criterion for the stability for the Z transform? Anyone? What is the criterion for the Z stability for the Z transform? No one? Abhishek Kumar, Jhansi, Tasneem, Rohan Garje, what is the criterion for the stability of the Z transform? That's correct. ROC must include the unit circle, and therefore which of these systems is stable? The only stable system is one in which the ROC is magnitude z less than 2, and that is basically the, if you can see, that is basically the anti-causal system, because when you have magnitude of z less than r min, that is basically a left-handed signal. So that is essentially the anti-causal system. Well, Balakrishna Khetani, ROC is not necessarily a ring shape. ROC can be either, it can be magnitude z less than r min, or magnitude z less than r1, r1 less than magnitude of z less than r2, or magnitude of z greater than r max, right? So out of these three, now in this particular case, the ROC includes the unit circle when magnitude of z is less than 2, and that is basically because it's of the form magnitude of z less than r min. This is basically an anti-causal system. So the anti-causal system is stable while the causal system is not stable. Okay, is that okay? Wonderful, wonderful, wonderful. Excellent. All right, everyone. So I think all of you had a good experience. Okay, thank you. So I think all of you had a good experience. I think all of you enjoyed this discussion, and the few problems that we tried to solve, hopefully they cleared some of the concepts, or either convolution or the inverse Z transform and so on. So yeah, I think so these should help you. So I think once thinking about these problems, solving such simple problems, and thinking about some of these things a little, you know, the trick aspects of the problem, I think that should help you get a better grasp of the concepts and help you solve problems with much more confidence, right? So I hope all of you have been able to enjoy this session, and I think we will stop here shortly. So if you have any quick comments, you can let me know. Otherwise, I think we will stop this session over here. Is that okay, everyone? All right, everyone. Thank you. Thanks very much for joining us. It was really fun. I think I enjoyed it. I hope you also enjoyed this discussion. Rohan Garje, I think this will be the only live session, but future, I mean, as is the case, you can solve all the assignments and the lectures, and I invite you to also participate in the exams. I wish all of you all the best for the exam. Those who are taking these exams, you should take the exam. Of course, I think the last date is probably over, or last date is over. So yeah, but I hope many of you are registered for the exam. Solve all the assignments, go in with confidence, and definitely you should be able to do well in the exam, right? I wish you all the best. All the best. Thank you very much, Rohan, Garje, Tasneem, Balakrishna Khetani, Jansi Rani, Sonia, and I think many of those who joined, Babi, Buddy, Rajeshwari, I think Mabinash Mohapatra, I think many of you have been able to join us. Thank you very much. Please do continue to participate. Please do let us know your feedback, and I wish you all the best. Thank you. Thanks very much. Appreciate it. Thank you.
Thank you so much, sir.
Thank you. My pleasure.
I'll just stop the broadcast, sir.
Yeah. No, it's very good. I enjoyed it. See, this Murli, and see, I'm facing a problem. Actually, I wanted to discuss this with you.
Yes, sir.
One professor